Yeah. Hello, everyone. It's wonderful to be here. Welcome. As you just heard, I came here by way of Canada, the newest 51st state of the United States. Oh, sorry, the proud independent nation of Canada. And I'm going to start this off, and I'm going to, in a bit, hand it off to Phil in 18 minutes or so. Okay, so we are here. I'm going to here to ask you a question. We're going to talk about the Big Bang. Not going to change the topic. Hopefully, this is going to be surprising, amazing, entertaining. You're going to learn something new. But I'm going to start you with a question. The question we're going to keep coming back to. What is the oldest thing you can remember? You can close your eyes, ponder for a moment, and think about the oldest memory that you have. So both Phil and I have done this exercise. The oldest thing I can remember is an outline of a room I cannot quite recognize, in a city I cannot quite recognize. I'm not sure what city it is, but likely it is the city of Tehran, where I grew up for the first 20 years of my life. Phil's earliest memory is when he was pretending to be a cat. This, I guess, big demon, I was going to say little demon, but big demon here is not Phil. Is actually Phil's cat, Erebus, who was the primordial, or the Greek primordial god of darkness. Okay, so these were our earliest memories. What about yours? What about everyone else's? We can all try to come up with our earliest collective memories. And the primordial universe is, in fact, where our story goes next. The earliest cosmic memories take us back around 14 billion years. So we can all try to gather our earliest memories of our ancestors, relics, everything that we can have, our archaeologists, fossils, everything, we put them together, and it's going to take us back around 14 billion years. Here is where things become fuzzy. We cannot quite remember what happened. Now, I cannot, probably you cannot, but we can all put things together and try to remember, but there seems to be a gap. This vital space we cannot quite remember. So, try to recover the memory of this era is a subject of both tonight's lecture and in our book, Battle of the Big Bang, the New Tales of Our Cosmic Origins. So we explore tonight the edge of knowledge. There is discovery, but there is also a hell of a lot of uncertainty and a hell of a lot of conflict, and that's why it's called Battle of the Big Bang. We're going to journey tonight through the battles where my colleagues and I fight over the nature of the Big Bang and what came before. How we might recover our lost memory, our earliest lost memories. And maybe we can pick a winner for the Battle of the Big Bang. So let's try to remember one of these early memories, not quite as early as the Big Bang, but this is actually the first battle, and in our book we go through even earlier battles, but this is a battle, something about 100 years old or so, between someone you know, Albert Einstein, and someone you may not quite know, or is not quite as famous, but is known as the father of the Big Bang, George Lemaitre, who happened to be a Catholic priest, so that's why he's known as the father of the Big Bang. Right. And we're going to come back to that in a bit. So Einstein and Lemaitre fought over whether the universe expands. So Einstein, of course, invented the theory of relativity, so he was a well-known figure across the world. And there came this relatively unknown figure saying that he doesn't know what his theory says. So Einstein responds, and I'm Canadian, so French is our official second language, but I'm not a very good Canadian, so my French is terrible, so pardon my French. But it says, vos calculus sont corrects, mas votre physique est abominable. So, okay, good, as funny as I hope it sounds to me. Which translates to, your calculations are correct, but your physics is abominable. It turns out if I give this to Google Translate, it says your calculations are correct, but your physique is abominable. Okay, I haven't met George Lemaitre, but yeah, Einstein might have been right on that too. But what was the fight about? So the fight was about the nature of space and time on the largest scale of the universe. So Einstein initially rejected the expanding universe, but in fact his theory of general relativity, or his theory of relativity, the one that his own had developed, actually predicted it, and that's what Lemaitre pointed out to him. So in Einstein's theory of relativity, gravity is not a force, but rather a manifestation of that space and time have a geometry of their own. So gravity is in fact the curvature of space and time. And this curvature is a dynamical object. So here, this picture up here, you see the sun and the earth, and you see this cartoon of how the space-time around them is curved. And the reason Earth goes around the sun is not that there's a force, gravitational force. In contrast to what you learn at the school, the reason Earth goes around the sun is not the gravitational force of the sun, but rather that the sun curves the geometry, and this curved geometry causes Earth that's trying to go on a straight path to actually curve around. So the Earth is doing its best to go on a straight path, but the space itself is curved, and that's why Earth goes around circular or elliptical orbit. So that's the story for Earth and the sun, and that's Einstein realized, but in fact, his theory implies something greater, that space-time is also a dynamical object, and it could expand and contract, the entire space, and not just a space around Earth and the sun. And that's what we come to next. But before we get there, let me introduce you to two characters. So the first one is here, Miss Henrietta Leavitt, who is known as a Harvard computer. So it's a computer before the computers that we know. In fact, it was a person. She was part of this group of women at Harvard College Observatory who actually did a lot of astronomical calculations that more, I guess, important astronomers were too busy to do. And there's something that Ms. Leavitt discovered, that if you look at certain type of variable stars, the brighter they get, the longer the duration or the period of their variability becomes. And it was a very powerful discovery because later, Mr. Edwin Hubble discovered that you could use this to measure the distance to distant galaxies. And in fact, that was the first time that we realized that we are not the only galaxy in the universe, but there are other galaxies like ours, but just much farther away. Moreover, he discovered something amazing, that these faraway galaxies that you could measure their distance, they're also moving away from us. You could do it by measuring Doppler shift from their light. And the farther away they are from us, the faster they're moving away from us. So that was amazing, because that was exactly what George Lemaitre had predicted from Einstein's mathematics of Einstein theory of relativity, that the universe is not static, it should be expanding or contracting. If it's expanding, then you exactly expect this relationship, that the velocity should linearly depend on the distance. The farther things are, the faster they move away from us. And this is now known as Hubble-Lemaitre law. Okay, so cosmos actually expands. Einstein 0, Lemaitre 1. So that's our preamble. But now that brings us to our first full-blown battle. And again, I'm going to ask you this question: what is the oldest thing you can remember? This time, we're going to remember Battle of the Expanding Universe. So Battle of the Expanding Universe is in fact, about the title of this presentation is about the Big Bang. But for everyone to be on the same page, let's define Big Bang. What's the Big Bang? So imagine everything, stars, planets, you and I, they're all packed into a hot, dense primordial plasma. Then boom, expansion begins. So that's your boom, that's your Big Bang, expansion begins. Something that video gets wrong is, in fact, Big Bang didn't happen at one point in a space, but happened almost everywhere at the same time, or let's just say everywhere almost at the same time. So as this universe expands, it cools, the gravity forms galaxies, a star, planets, and eventually life. So that's the story of the Big Bang. But that's the story we're telling you now. That's not the only possible story. The other way that the story could have unfolded is the diagram you see on the top. And that's actually the first battle of the Big Bang. So I told you the Big Bang cosmology, the universe was hotter and denser at the early times, and it expands, gets more dilute and less dense. But another possibility, which was very interesting and theoretically attractive, was maybe as the universe expands, there's just more matter that are created out of vacuum. And that's the top picture. You have more and more black dots. So this is you, and this is another galaxy. They're moving far apart, but then there are more galaxies created out of nowhere. So that's known as a steady state, and it's very kind of aesthetically pleasing because the universe has always been the same. It's expanding, but there's more matter coming. So it never really changes. We don't live in a special time. All times are like other times. So that was the first Big Bang, that first battle of a steady state versus the Big Bang. And on the left here, you see Professors Bondi, Gould, and Hoyle. Fred Hoyle, most famous person, he was a professor in Cambridge who was one of the most vocal champions of a steady state. On the right, you see Mr. Lemaitre, who we've already met, George Gamow, a Ukrainian physicist who was a theoretical physicist who developed a lot of the theory of the Big Bang, and Thomas Ryle, who was a British astronomer who came up with a lot of observations that ended up supporting the Big Bang theory. So what did so this is our recreation of the battle between Mr. Hoyle, Professor Hoyle, and Professor Ryle. It turns out that when Sir Martin Ryle observed the distribution of distant radio galaxies, he found that the farther away you look, the density of these galaxies becomes, they become denser, or the distribution changes over time. So that countered Fred Hoyle's steady state model and supported the Big Bang theory. And this led to a lot of heated exchanges between Ryle and Hoyle, probably not somewhere far from here, a few decades ago in the 50s and 60s. So famously, Woodruff T. Sullivan, a historian of radio astronomy, said Ryle and Hoyle would go after each other like a mongoose and a cobra, I guess. This is actually how the file looks like, I guess, yeah. You can see the resemblance. I'm not sure. Let you decide which one is which. But that battle was settled, at least for most scientists, when a discovery was made, and that was the famous discovery of the cosmic microwave background, the afterglow of the Big Bang. So in fact, George Gamow, who I already introduced to you, he, with his collaborators, showed that the hotter, denser universe would emit light, like the sun. So you should expect to see this light from the Big Bang. However, it wouldn't be as bright as the sun because the universe expands and cools down. So the radiation you see from the Big Bang would be cooler a little bit, by quite a bit, in fact. In 1965, Penzias and Wilson, who were researchers at Bell Labs in New Jersey, Bell's laboratory in New Jersey, discovered a uniform cosmic microwave background with a temperature of approximately 2.7 Kelvin or minus 270 Celsius. So this is a famous discovery, rightly so. They won the Nobel Prize for this important discovery, and that was basically the thing that convinced most scientists that Big Bang, in fact, is a more compelling theory than a steady state. However, this is not quite the correct story. In fact, cosmic microwave background was discovered 25 years earlier by a Canadian, Andrew McCullough, who is pictured here. He unfortunately died even before noticing that his discovery was confirmed or correctly interpreted because of cancer. But you can see this paper from 1940 that he actually measured the temperature of the molecules in the interstellar medium to be exactly 2.7 Kelvin, which is the temperature measured later, 25 years later, by Penzias and Wilson. So Canadian first discovered the CMB. Another example of us beating those Americans here. Go Canada. Very good. But now that we all agree that there is a CMB, no matter how it was discovered, let's talk a little bit about what it is. So the CMB is almost perfectly uniform, but if you increase the contrast, there are tiny temperature fluctuations or variations that you see within it. It's about a part in 100,000. You see these ones. And it turns out that these are really the fingerprints of the Big Bang. They're sound waves that were produced at the Big Bang. And you could also think of them as ancestors of galaxies. They're tiny ripples, but then over time, due to gravity, they grow, and eventually they make galaxies, planets, and stars. So in this picture, if you want to understand what it means, the CMB variations are these basically spots you see up here and down here. This bright red band here is actually the Milky Way galaxy. So this one is actually not primordial, but all these other things you see at the top and bottom are. Okay. So now we come to this question of basically, is it meaningless to ask what came before the Big Bang? So the Big Bang is often thought to be the beginning of time. So asking what came before the Big Bang must be meaningless, right? So I say is meaningless, but really, if you think it's the beginning of time, then there shouldn't be anything before it, right? The reason you would hear this very often and very widely is because of these things known as singularity theorems proven by famous scientists known as Penrose and Hawking. So they proved that there is a point, if you take the standard model of cosmology, and then this is kind of a cartoon that shows that. So here, this was, at some point, the universe was very hot and dense. It kind of expands, cools down. Here, around 375,000 years after this initial time, cosmic microwave background is emitted. And then slowly, these tiny ripples grow due to gravity, form the first stars and galaxies. And sometime, for some mysterious reason, around 5 billion years ago, expansion starts accelerating or speeding up. And then we live here, around 14 billion years after this initial point. But then what that initial point is really a mystery. And according to Penrose and Hawking theorems, there was a singularity. So, and that's what is a singularity. A singularity is a point where time stops. So basically, there's no way to push your equations beyond that point. So what are these singularity theorems? So they prove, so these gentlemen, Penrose and Hawking and Penrose you see here, they prove that with these four assumptions, if the gravity is always attractive, there are 3 dimensions of space and 1 dimension of time. There is no time travel. And if you use the mathematics of Einstein, which is basically the most important assumption, then there must be singularities. However, nowadays, most cosmologists, including Penrose and Hawking, these gentlemen themselves, eventually concluded that at least one of these assumptions must be violated. So there are really 2 Big Bangs. One is, can you spot, so there are 2 Big Bangs. I'm going to ask you, can you spot the difference between these 2? What's the difference? Anyone can tell? Yes? Oh, that's a different. Where did that come from? I don't know. Somebody. Phil, was that you?
They changed the update on when the estimate was.
Okay.
And they got more data.
That's a difference. But you have a very keen eye. I think, yeah, you're going to make a better cosmologist than anyone in this room. Okay, very good. Any other difference? Okay, there is a singularity. This word here, right? So basically, we have these two stories. One of them, there is a singularity. There's a point that time stops, and another one where we don't really know. And that's we call the hot Big Bang. In fact, we conducted a survey from leading physicists in Copenhagen last year. Out of 12 questions about basically controversial topics in physics, there was only consensus on one, that the Big Bang is not. So basically, only 11% thought that Big Bang was the beginning of time without a singularity. 6% thought Big Bang was the beginning of time, and there was a singularity. But 68%, a whopping 68% thought Big Bang has nothing to do with singularity. It just says that universe was hotter and denser than early times and just decreased now in temperature and density. So what came before the Big Bang is not really a meaningless question. Now, the person who's been asking this question from a lot of cosmologists is my collaborator, Phil. He's been interviewing many people, including the famous Stephen Hawking, Professor Roger Penrose here, and me. Somehow I managed to fit in. This is where I first met him when he visited our institute. He wanted to talk to me about the model that I was working on. And this was the video I was in, and this is Monica, his wife, who's been narrating all of Phil's videos. So she should really get all the credit for this, I think. And here is Phil.
Okay. Well, thank you, Niyayesh. Let me say what an honor it is to be here and take you through our next battle, the battle of inflation. So the Big Bang's been very successful, but it has its problems. These are 4 that are commonly quoted. Now, don't worry, we're not going to have time to go over all of them. So I'm just going to talk about one of them, the horizon problem. And let's think about eating a yummy pizza. So when a pizza comes out of the oven, it cools to the temperature of the room. And we enjoy its warmth because this takes time. It can't happen instantly. But the cosmic microwave background, it has the same temperature absolutely everywhere, wherever you look on the sky. And in 14 billion years, here's the weird thing, there hasn't been enough time for the CMB to come to equal temperature. So how did it get to be so uniform? It's like the pizza came out the oven and instantly cooled down. That can't happen by the laws of physics. So this is the horizon problem. And a solution comes in the form of inflation. So the idea here is the universe expands exponentially. So it would double in size. The estimate is something like 10 to the minus 37 seconds. So if you don't know what that means, it's just a really, really short period of time. And we would only need 100 of these doublings to solve all 4 of those problems of the Big Bang, including the one that's our subject matter for tonight, the horizon problem. So how does it do this? Well, in an inflationary universe, the cosmos would be vastly smaller 14 billion years ago than in the standard cosmology. So particles can come to equal temperature because they're traveling a shorter distance. So cosmologists are very, very impressed with this theory. It's mainstream. This is Alan Guth, the inventor of inflation. He's winning the Dirac Prize here along with his colleagues, Paul Steinhardt and Andre Linde. They helped develop the theory after Alan Guth invented it. And you can see it in textbooks. You might see something, a picture. This is the timeline of the universe. We have the Big Bang, then cosmic inflation, then we go to a normal expansion. But when I interview cosmologists, they tell me this picture that you'll find in all the textbooks is actually wrong. Because inflation is a pre-Big Bang model. But how can that be? Didn't time begin at the Big Bang? Well, recall that cosmologists now define the Big Bang as the hot Big Bang, the theory that says the universe evolved from a hot state. But inflation cools the universe to as cold as it could possibly be. And then when inflation ends, its energy has to go somewhere. So it goes into making matter and radiation. So that is the Big Bang. So it's not Big Bang, then inflation, no. It's inflation, then the Big Bang. And Alan Guth himself said inflation is a prequel to the conventional Big Bang picture. So that is pretty strange. We've got now a pre-Big Bang model, but it gets even stranger because this inflation, it doesn't end everywhere at once. Like radioactive decay, it happens with a half-life. But the part that hasn't decayed, think about that. What is it doing? Well, it's undergoing exponential expansion. And that's going to make more Big Bangs. And this repeats endlessly. So inflation doesn't make one universe, it makes a multiverse. And that brings us back to the battle that Niyayesh mentioned between the steady state and the Big Bang. And so, just to refresh your memory, I'm going to read a short poem about that battle. Said Hoyle, you quote Lemaitre, I note, and Gamow. Well, forget them, that errant gang and their Big Bang. Why aid them and abet them? You see, my friends, it has no end, and there was no beginning, as bondy gold and I will hold until our hair is thinning. Not so, cried Ryle, with rising bile, and straining at the tether, for galaxies are, as one sees, more tightly packed together. You make me boil, exploded Hoyle, his statement rearranging. New matter's born each night and morn. The picture is unchanging. And it's that last line of the poem that I want you to focus on here. The picture is unchanging. Because at the larger scales, eternal inflation is also unchanging. So replace the galaxies of the steady state model that were popping into the expanding space with these what are called pocket universes. And it looks very, very similar to the old steady state. Don't take my word for it. This is what Alan Guth said. He said, eternal inflation will strongly resemble the old steady state model of the universe. So there's a sort of irony here. Inflation sort of solved the Big Bang's problems, but then it brought back its rival through the back door. Now, another interesting implication is that inflation would imply gravity can be repulsive. I mean, we're used to the idea it's attractive, but inflation is actually driven by a repulsive gravity material. So that violates the singularity theorem that proved a beginning of time. But can inflation be eternal into the past? Well, one group said no, it cannot. It's only future eternal. It has to start somewhere. Another group recently said yes, it can be past eternal and also future eternal. And another group said maybe. We're not really sure. And in fact, the lead author on this last paper is none other than Niyayesh's wife, Ghazal. So we're not sure if inflation needs its own prequel, but it certainly is a prequel to the standard Big Bang. But not everyone likes prequels. So there's been something of a rebellion, and it's been led by Paul Steinhardt, you see in the middle here. Remember, he was one of the fathers of inflationary theory, but now he's turned against it. And he's teamed up with Anna Eas and Avi Loeb, and they wrote some very aggressive articles attacking inflationary theory. What you see here is from the Scientific American. That prompted dozens of scientists to complain. They wrote a letter to Scientific American. But what are their objections? Well, one is that there's too many inflationary models. I mean, I couldn't even fit all the inflationary models on the screen here. How are there so many? Well, there's just different ways that inflation can work. And this challenges the notion that inflation can actually predict the patterns of the hot and cold spots in the cosmic microwave background. Often you'll see in textbooks that inflation matches all this data very, very perfectly. But you could ask, well, which one of these inflationary models matches the data? So that's one problem. But having interviewed the critics and the defenders of inflation, I think I can say the thing that divides them most is this issue of the multiverse. Some really love it. I don't know if you like that movie, but they like the multiverse. Others, not so keen, even saying that it threatens the integrity of physics. So I interviewed Avi Loeb, one of the critics, and he does not mince his words. He said that he compared the multiverse to taking recreational drugs. You will feel good. I'm sure Alan Guth feels really good about the idea of the multiverse, but doing physics is not about feeling good. But Avi is actually no stranger to controversy. You might have seen him in the news. He's the Harvard astronomer who claimed that Oumuamua, an interstellar comet, is actually an alien spacecraft. So maybe the allegation of drug taking can go both ways. So I put some of the criticism to Alan Guth that they did, inflationary cosmologists have abandoned science, and he didn't mince his words either. He said, to quote, "To assert that I claim that science needs to abandon the concept of empirical testability, in my view, is a blatant lie." So getting these people together, not easy. I did finally get Roger Penrose, who's another critic of inflation, to have a debate, so that was a lot of fun. That was on my YouTube channel. But obviously, we don't think scientific disputes are settled on YouTube. But rather, what we want to do, or at least what inflationary cosmologists want to do, is to find the smoking gun of inflation. Is there such a thing? Well, inflation is thought to produce ripples in the fabric of space-time because of this violent expansion. And these are known as gravitational waves. And these might imprint onto the cosmic microwave background, making subtle patterns, swirling pattern called B modes. And detecting them is thought to be our smoking gun. Now, in 2014, you may have seen headlines saying, "We found it. We found the smoking gun of inflation." There was talk of a Nobel Prize for Alan Guth and Andre Linde. In fact, I asked Paul Steinhardt whether he'd accept a Nobel Prize for inflation, given he's now turned against it. And he did stick to his gun and say, "No, I wouldn't." But the Nobel Prize Committee didn't have to worry because that turned to dust. You see, it turns out that in interstellar space, there's lots of dust. This is a picture I took of the Wizard Nebula, and you see these dark patches. This is interstellar dust. And the BICEP team that claimed this discovery, they just didn't take account of the dust properly. But nevertheless, inflation is mainstream. And I think if these guys want to dethrone inflation, they're going to have to come up with an alternative. So I'm not going to have time to go over any in depth. I'm just going to do a very quick sketch. But one alternative is a cyclic universe. So its claim can mimic some of the effects of inflation. And some versions, the universe expands and contracts. But it doesn't have to do that. Roger Penrose has a model that never contracts. What happens is the universe at the Big Bang, because of the extreme conditions, can't build rulers or clocks. And that was the second assumption of the singularity theorem. So what happens is it loses its sense of scale, and then it transforms from one eon to another. Another option is the universe might come out of a black hole. Some of these models have inflation, but Niyayesh has actually made one that was on the front cover of Scientific American that doesn't need inflation. And then the last option is called variable speed of light theory. So here, it's proposed that it's not the expansion rate that was incredibly high in the early universe. Rather, it was the speed of light. So we break Einstein, and that again could mimic inflation. But if inflation happened and it had a beginning, we can still ask, what came before? And one suggestion is what's called the no boundary proposal. This was proposed by Hartle and Hawking, and what they did was take quantum physics, that's the physics of the very small, and they applied it to Hawking's singularity theorem. And something really weird happens. Time turns into space. So instead of having 3 dimensions of space and 1 of time, we have 4 dimensions of space and no dimensions of time. And this could remove the singularity. So there's no single point of origin. But this quantum cosmology, I think it would require a deeper theory of physics. And to explain how that might work, I'm going to turn it back to Niyayesh.
Thank you, Phil. So, are your minds blown yet? No? Yes? Okay, for those of you who still have some mind left, we have one more thing, or a few more things. So still, we want to discover our earliest memories. And if you try to really think far back, we end up with battle of quantum gravity. So what is battle of quantum gravity? So it turns out we have these two fundamental tenets of modern physics, the most successful theories that humankind has ever managed to come up with. On the one hand is quantum theory, which is how you build your cell phones, your computers, how you can hear me through the, through the microphone. So these are all based on quantum physics and how engineers manage to use the rules of quantum physics to make all advanced technology that we use. So that's incredibly successful, incredibly precise. On the other hand, we have theory of gravity developed by Einstein, general relativity, that on its own right is incredibly successful. GPS satellites have to use it, otherwise the rulers and clocks don't work right, we cannot get our position right. And in fact, we have even managed to detect gravitational waves or black holes that are pictured here that are predictions, very, very successful predictions of Einstein's theory of relativity. There's only the problem that these two sets of rules don't work together very well. So Einstein is to blame here. He was, in fact, at the heart of developing both of these, but then somehow he turned against quantum mechanics in his later years, and indeed, there is a problem. So there are different ways of talking about this problem, but this is the way, my favorite way. So there's Heisenberg microscope versus Einstein microscope. So I want to kind of demonstrate the contradiction between these two theories. So on the left-hand side, I have the Heisenberg microscope. So those of you who recognize this gentleman, I'm going to come back to that in a minute. So in Heisenberg's picture, who was one of the founders of quantum mechanics, particles are the same as waves. And the higher the energy of a particle, the shorter is the wavelength. X-rays have shorter wavelengths than optical photons, shorter wavelength than radio waves, for example. So if you want to see something really, really small, you want a very short wavelength, that means very high energy particles. So higher energy particles give you better resolution for a Heisenberg microscope. On the other hand, for an Einstein microscope, the higher energy particles, higher energy means higher mass, that leads to bigger black holes, and actually gives you worse resolution. So in this sense, these two theories gives you contradictory results. That if you want to make a better and better microscope, one of them tells you need higher energies, the other tells you need lower energies. Higher energy actually makes it worse. And incidentally, this picture is the first came up with when I Googled Heisenberg a while ago. I'm not sure how many of you recognize this guy, but I thought since this was good looking that this one, so I just used this picture. Those who do recognize this, he's an actor in a famous TV series about 10 years ago or so. And it turns out if you know the plot of the movie, he's accused of drug dealing. But it turns out he's not the last scientist accused of dealing drugs. And in our book, we talk about another scientist, a cosmologist for the Big Bang model, who's accused of dealing drugs, although he vehemently protests that accusation. Okay, so, but moving on. So what's the deal with what happens, actually, you combine these two theories? It turns out that all the predictions go berserk, basically, if you approach the singularity. As you increase the temperature and you try to use the rules of quantum mechanics and gravity together, they give you contradictory results, and these get bigger and bigger. By the time you reach this temperature of 10 to the 32 Kelvin, which is around 1 billion trillion degrees, if you want, it doesn't matter Celsius or Fahrenheit. By the time you get there, then basically you get just infinity from all your results. You kind of keep calculating and calculating, you keep getting bigger and bigger results, basically. So the theory just stops making sense at that point. And that's where we need a real theory of quantum gravity. That's basically as we are approaching that singularity, when things become very dense and hot. So you may ask, okay, so do we have a theory of gravity, quantum gravity? I have good news. We have actually many theories of quantum gravity. We have a zoo of theories of quantum gravity. So I have some of them pictured here. It's not easy to learn a lot about them from these pictures. But basically, the short of it is that these are different theories for microscopic structure of space and time, which is kind of the idea is like if you zoom in here in the air, it looks like something that's smooth, but if you zoom in, you see molecules and atoms and things like that. So the space-time, the idea is the same. If you kind of zoom in with a very, very powerful microscope, you're going to see something. And these different theories predict different kind of structures, different mathematical structures with different properties. So we don't have time to go over all of them, but I'm going to mention two of them. A string theory, which is in fact the most popular proposal. So it replaces point particles with the strings. All these infinities, the infamous infinities, they become finite. And then gravity is also one type of vibration on these strings. Other particles are also other vibration of the strings. There is only problem. This theory, to be mathematically consistent, it needs 6 extra dimensions in addition to the ones that you see. And also it requires supersymmetry, which is basically saying every particle has some sort of an evil twin that we don't see either. So that's the problem. So we don't see either of those. In fact, there is a third prediction, which is maybe dark energy should be negative, but that's a little bit more controversial. The rival, at least one of the rivals, is loop quantum gravity. That says a space is discrete. That means it cannot be divided to smaller pieces. That's kind of a cartoon of that there. It cannot be infinitely compressed, so it avoids the singularity. There is no extra dimension, no supersymmetry, so that's good. But then it doesn't really explain other forces other than gravity, other properties of nature. So it only explains gravity, no electron, no photon. So those are kind of more add-ons later on. So if you're wondering how the debate between these two go, I have an example.
You agree with me, right? Loop quantum gravity is the future of physics.
Sorry, Leslie, I guess I'd prefer my space stringy, not loopy.
Well, I'm glad I found out the truth about you before this went any further.
Truth? What truth? We're talking about untested hypotheses. It's no big deal.
Oh, it isn't really? Tell me, Leonard, how will we raise the children?
I guess we wait until they're old enough and let them choose their own theory.
We can't let them choose, Leonard. They're children.
Okay. There you have it from the famous Big Bang Theories sitcom. If you're interested in a slightly more realistic debate between proponents and opponents of these theories, you can go to Phil's YouTube channel. And then he has hosted a debate between Carlo Rovelli, who was one of the founders of loop quantum gravity, and David Gross, who was a famous Nobel Prize winner and a pioneer of a string theory. Apparently, I've been told that according to post-debate poll, Carlo Rovelli won the debate, but you could go and watch it and decide for yourself. And of course, as Phil mentioned, science is not decided based on YouTube channel debates. Okay, so how do we do cosmology with these things? There are many ideas with the string theory. You could have universe that lives on brains. So because it's extra dimensions, somehow we need to get 3 dimensions, so maybe we are confined to these lower dimensional things. And then when they collide together, we get a Big Bang. That's known as a pyrotic universe. So that's an idea. Seems speculative, but people have written lots of papers on this. There is a string gas cosmology. So the idea is that maybe the Big Bang was not a hot gas of particles, it was a hot gas of strings. And then as you approach the singularity, that actually prevents it from happening because these strings start doing weird stuff. And then there is a holographic cosmology, yet another proposal which I worked on in the past. And it suggests that as you approach the Big Bang, maybe you lose 1 dimension. And in fact, in that case, the dimension you're losing is a dimension of time. And we developed and kind of tested the mathematics for this particular proposal that's motivated from a string theory. In fact, the founding father of string theory, Gabriel Veneziano, argues that basically the beginning of time is a myth. He had his own pre-Big Bang model from string theory. And in fact, many Big Bang proposals agree that there was no beginning of time. An example of that is a rival to string theory, loop quantum cosmology, or loop quantum gravity. So these are the three founders of loop quantum gravity. Leah Smolin is my colleague at Parameter Institute, Abhay Ashtekar at Penn State, and Carlo Rovelli, who you already met. And they basically asked this question of singularity, whether it's actually replaced by a big bounce in loop quantum gravity, which is this discrete space idea. Now, Abhay Ashtekar is a firm yes on this. Another well-known loop quantum gravity researcher, Martin Boyewald, who is a colleague of Ashtekar at Penn State, says no. So there are interesting battles and debates within that community that we cover some of it in our book. But here we're going to just move on from that. But in fact, that's not the only way you can get a bounce. We just really need repulsive gravity. And in fact, one possibility for that is from this theory that we call Kaskutan, that was developed by Ghazal, who you already met, my wife. And she showed that if sound waves could travel infinitely fast, then this idea of repulsive gravity actually could make sense. And there are these so-called instabilities that are problems, that things that blow up with repulsive gravity, which is in fact don't happen if sound waves can travel infinitely fast. So this actually led this to the idea of Kaskutan bounce. And here is an example of the calculations that she did with her students, where everything kind of goes as smoothly through this bounce. There's no singularity, nothing blows up, everything is very well. So this idea of bounce is in fact very prevalent in Big Bang alternative models. And what they all suggest that Big Bang was not the beginning. 14 billion years that you hear everywhere is only a lower limit on the age of the universe. Universe could be older, in fact, infinitely older, even though we don't exactly know what happened there. And in fact, quantum gravity is only one way to avoid singularities. There are other ways to do that. And that brings us to our next battle. That's battle of time machines. Remember, one of the loopholes in singularity theorems was that there should be no time machines possible. But is that true? Could we have time machines in our universe? So there have been famous solutions in Einstein's theory of gravity where there are actually time machines. You all have seen them, you've heard about them in science fiction movies. And there are, in fact, serious scientific peer-reviewed papers on time machines. However, if you add quantum theory to the story, things become complicated. In fact, Stephen Hawking firmly was on the no camp. He thought that if you add quantum theory, time machines cannot be possible. They are inconsistent with quantum theory. But on the other hand, my old professor at Princeton, Richard Gott, who I can, in fact, I worked with, well, I was his actually teaching assistant when I was at Princeton. So I like him, and he actually really liked time machine. He actually written books on time machines, and he has these explicit examples which show that quantum theory works perfectly fine in the spaces with time machines. And if he's right, then our universe could be, at least parts of the universe could be like a Groundhog Day, that we're stuck in a time loop and everything happens over and over and over again. Okay, so that's a possibility. So this is a picture from their model, Gott and Lee model. Lee was a graduate student when I was there at Princeton. So they worked together, and they came up, they showed basically a model like this could be a correct model, a potential model or a universe where you have a time loop in the beginning. So this is a space-time. Universe basically creates itself, and at some point you come out of the loop, and then here the eternal inflation that Phil was showing you. So that's one way that there could be time machines in the universe. And in this case, there is no singularity. Universe can create itself. An alternative is one that I developed with my student Beth Gould a while ago, where the entire universe is, in fact, a time machine. And then this is a great animation that Chris, Phil's friend, made, where you start from the Big Bang. The universe is expanding. It creates the cosmic microwave background. It is released at this point. There are galaxies, planets, everything. Universe then accelerates, cools down, all the galaxies die. And at some point after you wait infinitely long time, this this evolution just matches back to itself. So we actually mathematically showed that the entire history of the universe could actually map back to itself. The entire universe could be a time loop. So you might have heard about Nietzsche's eternal recurrence, where he believed that everything just repeats over and over again forever. And so that is actually a physical or cosmological possibility according to this scenario. So it's not just religion that promises an afterlife. It could be science, and this duality brings us back to our penultimate battle, which is science versus religion. And in fact, the person who has explored this boundary and what science and what religion and where they can mix and where they cannot is, again, our own Phil Halper, who is going to have the podium back now.
Thank you. It's pretty hot in here tonight, right? Oh yeah, so we're going to turn the temperature up. Because we're going to talk about the battle of science and religion.
Yeah.
But the first thing I want to do is talk about the religion within cosmology. Because you can take the cosmologist out of religion, but can you take the religion out of the cosmologist? Can we ever rule out string theory, loop quantum gravity, or inflation? And without empirical evidence, I think there's a real danger that these theories can calcify into dogmas, just like we saw in the sitcom The Big Bang Theory. We don't want that, but there is a way out. What we need is our theories to make precise predictions. So this is actually from Niyayesh's time loop model, and they were able to calculate what the cosmic microwave background would look like. So that's what we want from our theories. But there's also the cosmology within religion. Can the Big Bang prove God? As we saw, the father of the Big Bang was a Catholic priest. So you might think he would say yes. But actually, he said no. He wanted to keep his science and his faith quite separate. But not everyone agrees with him. This is William Lane Craig. He's a philosopher, and he says yes. And he's revived an old argument for God in the light of Big Bang cosmology. It's called the Kalam cosmological argument. So it goes like this. Premise 1, everything that begins to exist has a cause. Premise 2, the universe began to exist. Therefore, the universe has a cause. And then he has some arguments to say, well, that must be God. And Craig uses the Big Bang to defend premise 2. But what I hope we've shown you is that we don't know if the Big Bang was the beginning or not. Might have been, might not have been. We don't know. So we can't really say premise 2 is right. And also, we don't know if causality is fundamental. In quantum mechanics, there's a lot of debate whether there actually is causality. So we don't know if premise 1 is true. So I don't think we should be buying this argument. But I don't want to tell you there couldn't be a God, just we shouldn't use the Big Bang to try and prove it. And one idea that I think is kind of fun to think about is, could we make a universe in a laboratory? Well, Fari, Guth, and Guven studied this, and they said, yeah, it might be possible for some super advanced civilization. And what's fascinating about this is that if you could do it, then the universe you create would actually pinch off from your space. The expanding space would not invade your space. And it would appear to you as a little black hole. You could not get inside it. You couldn't give moral commands to any of the people that you created. And there'd be no reason to think that the creator would be a perfect being. I've interviewed Alan Guth, spent many times with him, and he's a really nice guy, very smart, obviously, but he did win an award for having the messiest office in Boston. So if you were to create a universe in a lab, would you sign your name like a painter does on a painting? Well, let's look at the cosmic microwave background. This is the oldest picture of the universe we can take. Can anyone see any initials here? It's the sign of a painter. Anyone? No? I think I see SH. Let me help you if you don't see it. Anyone? See it now? Yep, so SH is right there. Maybe then Stephen Hawking created the universe. Maybe he was wrong about time machines. He went back in time and created the universe. So there's another argument that sort of mixes cosmology and religion. This is called the fine-tuning argument. And the claim is that if the constants of nature, like the masses of particles, were even slightly different, life would not exist. So how did we get so lucky? And we're told that we have to believe either in a multiverse, because if you buy lots of lottery tickets, well, one of them's bound to win, or we have to believe in an intelligent designer, because maybe he could sort of put the dials just right and make the universe okay for life. So Niyayesh, actually, we did this survey of all these controversies within physics. I thought it'd be fun to show you actually what physicists think about this. So the most popular answer, what do you think? A or B? Multiverse or designer? Okay, well, actually, it was neither. They said it was brute facts. That's the explanation. So what does that mean? It means the constants are what they are. There's no further explanation needed. And maybe you could justify that as saying, well, look, if I get a lottery ticket and it wins, I'm going to be very surprised. And I'd be justified surprised because I know how lotteries work. But we don't know what sets the constants of nature. We have no idea why they have the values that they have, so we can't say that they are improbable. The multiverse was the second most popular option. But the third one, I think, is quite an interesting one. It says, well, maybe black holes could give birth to new universes, and then they might inherit the properties of their parents. We'd have something very similar to Darwinian selection, and we'd select for life-permitting universes. The other one is that the constants are necessary. So think of stars, planets, people. We know their masses can vary, but for the constants of nature, like the mass of the electron, we never, ever, ever see it vary. So maybe it just has to have the value that it does. And the last option was an intelligent designer. But is this science? I mean, there's a lot of speculative ideas here. How do we tell the difference between pseudoscience and science? Well, unfortunately, there's no exact demarcation criteria, but I kind of like this quote. It's from the theoretical physicist Richard Feynman, and he said that the game I play is a very interesting one. It's imagination in a tight straitjacket. So the straitjacket is the data, the observations that we make about the universe. So new data can sort of tighten Feynman's straitjacket. And the hope is that it will tighten it so much as we get new data that we could actually reveal a winner in the battle of the Big Bang. And to explain how we might actually go and do that with fantastic new technologies, I'm going to hand it back to Niyayesh.
Thank you, Phil. So we are at the last stretch. We're going to declare the winner, maybe. So this is our final battle for the oldest thing you can remember. So I'm going to start with a slightly tangential prelude. So when we were finishing our book, I wrote that the scientific method reaches its pinnacle in understanding the Big Bang. And that once honed, it can help solve humanity's greatest challenges. Now, Phil challenged me. He said, but can really science solve all the problems? What those wars? Can science solve the wars? I kind of said, maybe. I argued, as a scientist does, very abstractly, that because we are part of the universe, science can help us understand ourselves better. Maybe that helps us solve wars. But even to me, that sounded too abstract, maybe too academic. Not anymore. So today, the very forces working to define science to cancel my universities, Princeton, Harvard, and beyond, are the same ones fueling endless wars. So bombs raining down on my home country, my hometown, my uncles, cousins, aunts, bombs that seek not to just kill, but to erase memory itself. And make no mistake, for every successful bunker buster mission, destroys a mission to understand the cosmos, not just in our balance sheets and budgets, but in our very souls. And here on the right, you actually see a list of all the canceled missions with the new budget that presumably is more balanced, but of course has enough room for all sorts of endless wars. But then, is there another way to make progress? So the final battle, I think, is not maybe to fight amongst each other, but let the universe guide us. The wonderful stuff we talked about, the sound and geometry waves that come from the Big Bang, the subtle patterns in cosmic microwave background, the largest scale distribution of galaxies, these are the clues that eventually guide us to tell us what actually happened at or before the Big Bang. So we talk about various wonderful missions that, if funded and funded properly, they could help us address these foundational questions. Like the distribution of galaxies, this is a spheric satellite, which is a NASA mission, and it's going to map hundreds of billions, if not trillions of galaxies across billions and billions of light years. And by studying the patterns of these galaxies, we can rule out some of the models of the Big Bang. But even more exciting than that are these waves of geometries, gravitational waves that Phil talked about. These are ripples in the fabric of a space-time. They have been actually detected triumphantly for black hole mergers across the universe. And now we actually see them, well, not quite this extremely, rippling Earth. And then there are these famous detectors, LIGO detectors in the United States, and there is one in Italy that actually can measure these ripples by interfering lasers across kilometers of scales. So these are not gravitational waves from the Big Bang, but there could be gravitational waves that are generated at the Big Bang. And as Phil mentioned, inflation actually shows that some models of inflation actually show that there are gravitational waves. Other models of inflation and alternatives like cyclic models don't produce them. And if we could detect them, then we can rule out some of these models. So we are looking for these gravitational waves from the Big Bang using the cosmic microwave background. This is Simon's Observatory in Atacama Desert in Chile. It's going to turn this picture to something with 10 times better resolution. Maybe you could see the gravitational waves there or the effect of gravitational waves. This is a Lightbird satellite by Japanese Space Agency that may potentially detect the effect of gravitational waves on the CMB from the Big Bang. And maybe we could directly detect these gravitational waves by a mission like the Big Bang Observer, which actually sends out powerful lasers in the solar system across tens of thousands of kilometers. They're sending lasers to each other, and they could measure gravitational waves at enough precision that they could basically rule out some of these inflationary models. So to end our journey, the final battle is not really amongst our colleagues, me and my colleagues. Of course, I do have a lot of things to complain about my colleagues, but that is not really the final battle. Or our battle amongst ourselves, countries, nations. Our true struggle is to overcome our ignorance, our adventure to comprehend the cosmos, ourselves included. So our process is the scientific method, which is honed on solving the greatest mysteries of the cosmos, but also derived from all other aspects of our humanity. We cannot really separate science from religion, from art, from literature. So those are all part of the scientific process and scientific method. So this will be our ultimate survival tool in an ever-changing world. And I'm going to leave you with the last word, that the power to remember our past lies in your future. It's up to you to decide what you want to do with that power. Thank you.